Hi guys, welcome back to another kinematics video. This is our second video in this unit, and today we're going to be talking about what happens if our velocity is not constant, kind of picking up where we left off last time. So if our velocity is not constant, if it is changing, then we're going to need to introduce a new term here. This term is acceleration. Acceleration means a change in velocity over some period of time. So our definition for acceleration is, we're going to use the letter A, the lowercase letter A, to be our variable for acceleration. It is equal to a change in velocity over some interval of time. Okay? And it's going to have a direction associated with it, meaning it's a vector. Okay? Acceleration is a vector, and our definition is change in velocity over time, delta v over t. Okay? All right. But now, what are the units for acceleration? Well, we can actually figure this out just taking a look at this equation. So when we want to find out the units for something, we can use a little bit of algebra the same way we use algebra with variables. So if I want to know the units of acceleration, that's why I'm putting the brackets here. If I want to know the units of acceleration, then I'm going to just take the units of velocity and divide them by the units of time, because my definition of acceleration is velocity over time, or change in velocity over time, rather. And so all I have to do is put my unit for velocity on top, which is meters per second, and my unit for time on the bottom, which is seconds. And so if I go ahead and take meters per second and divide it by seconds again, I'm going to end up with 2 seconds on the bottom, or a second squared on the bottom, aka meters per second squared. And that is my unit for acceleration, meters per second squared. Okay, so in review, acceleration is a vector that is a change in velocity over time, and the unit for acceleration is meters per second squared. All right, so how are we going to use acceleration though? Well, we're going to be using acceleration in a few of our equations here. We're actually going to introduce 4 kinematic equations right now that we'll be using a lot for the rest of the unit. So you're going to get very familiar with these 4 equations. There are 4 crown jewels of kinematics, and they work really well anytime we have acceleration and constant acceleration, because we're always going to be working with constant acceleration in kinematics. So let's go ahead and derive these units for, or these equations for kinematics, because I don't like to pull things out of thin air in physics. And the beautiful thing about physics is I can introduce things that you already know, and from those things derive equations, and we can use those practically. So let's go ahead and start with the first kinematic equation. Okay? First kinematic equation. And in order to derive this, I'm going to start with our definition for average velocity, which, if you remember, was change in position or displacement over time, right? We said average velocity was delta x over delta t, and then we multiplied both sides of the equation by time in order to get our constant velocity equation, which looked like this. Okay, looked like that. But now I want to kind of modify this equation, and if I'm working with a constant acceleration or a constant change in velocity, that means that my average velocity over some interval is going to be the average of my initial and final velocity. Let's see what I mean by that. Let's say we have a graph and we are graphing velocity and time on this graph. All right, this is a velocity versus time graph, and I have a constant acceleration. And my acceleration is going to be my change in my velocity over time, aka my slope of this graph. So let's say my acceleration is some constant like this, okay? Now let's say I'm taking the average velocity over some interval. Boop. I'm going to take the average velocity over this interval. What is my average velocity? It's going to be somewhere here-ish, right? It's going to be halfway in between. How do we know that? Well, the average of two numbers, the average of two numbers is just those two numbers added and divided by 2. So if I want to find the average velocity over this interval, I just have to take the initial velocity that we're starting with and the final velocity that we're starting with and add them together and divide by 2 to get my average velocity for this segment, okay? So we know that our average velocity for any interval is equal to our initial velocity plus our final velocity divided by 2, provided that the acceleration is constant, okay? Provided that we have a straight line here, a constant slope. So I'm just gonna go ahead and replace v bar in this equation, or average velocity, with this v initial plus v final over 2, okay? I'm just gonna go ahead and totally replace v bar times t, okay? And now I'm just gonna do a little cleanup work here, just to put it into a form we like. I'm gonna pull out the 1/2, just because it looks a little bit nicer, and that's traditionally how this equation is written. Okay, we have delta x, or displacement, is equal to 1/2 times the initial velocity plus the final velocity, in parentheses, times time. And this right here is our first kinematic equation, okay? Boom. Kinematic equation number 1 right here. Okay, that's cool. Now let's do the second one. All right, and the second one is going to start from a similar place, except we're going to be working with acceleration to begin with this time. Okay, acceleration we know to be change in velocity over time. So again, I'm going to multiply both sides of the equation by time to get change in velocity is equal to acceleration times time. Okay, same first step as we took last time. And now I'm going to separate my delta v, my change in velocity, into final and initial. And if you remember from last time when we talked about displacement, that a change in a variable is equal to the final minus the initial. So our change in velocity is just our final velocity minus our initial velocity. That is equal to acceleration times time. And I'm just gonna move over my initial velocity over to the other side of the equation by adding it. And I am going to get this equation. Velocity final, the final velocity, is equal to the initial velocity plus acceleration times time. And that is my second kinematic equation, okay? So we already got our first two. Now let's do the third one next. And we're actually gonna be starting off with the two equations we just derived, okay? We're going to use our first kinematic equation, which was this, okay? And we're also going to use our second kinematic equation, which was this. All right. Okay. And what are we going to do with these? Well, what we're going to do is we're going to try and eliminate final velocity in the first equation, okay? We're going to try and eliminate final velocity. And what I mean by that is we're going to replace final velocity with this definition for final velocity. We know that final velocity is equal to initial velocity plus acceleration times time. So we're totally allowed to replace final velocity with v initial plus at because it's the same thing. So let's go ahead and do that and see what happens. We're going to get delta x, displacement, is equal to 1/2 times, in parentheses, v initial plus what this part here in red. So we're going to have another v initial from that plus acceleration times time. Okay? All that times time. Let's clean up inside the parentheses a little bit because we have a couple like terms that we can combine here. So we're going to get 2v initial inside the parentheses plus acceleration times time. Cool? All right, now I'm going to go ahead and distribute the 1/2 through this equation, and I'm going to get v initial plus 1/2 at. Okay, so if I multiply 1/2 by both of the terms inside that parentheses, Then finally, I'm going to do the same thing with time. I'm going to distribute the time through. I'm going to multiply both terms inside the parentheses times time. And so I'm going to go ahead and get this magnificent equation. Displacement, delta x, is equal to initial velocity times time plus 1/2 times acceleration times time squared. And this is my third kinematic equation, all right? That's where the third one comes from. So we have 3 equations to play with, all right? And we're going to do the fourth in a second. And I'll also explain, if you are wondering at this point why we need these 4 equations, why do we need 4 different equations, you will see the practical use of each one of these 4 equations. They each serve a different purpose. But I would also like to point out something interesting here, okay? Hidden in this equation is a very special friend of ours that we've seen before. So, if, let's say, we decided that actually our velocity is not changing, okay? Our change in velocity is 0. We're working with constant velocity. What's going to happen to this equation? Well, if we're working with a constant velocity, there's just one constant velocity that we're working with, then our change in velocity is equal to 0, and thus our acceleration, which is equal to our change in velocity over time, right? That is also equal to 0. So because acceleration is in this term, this whole term is going to go to 0. And we're just going to be left with delta x equals v initial t. But wait, we don't even have to call it v initial because there's no initial velocity or final velocity. It's all one velocity. We can just call it our velocity because it's at a constant velocity. And look, it is our friend, the constant velocity equation. It's kind of hidden in this third kinematic equation, okay? All right, so on to the last one, on to the final fourth kinematic equation, and we're actually going to start from the same place that we started with the third, okay? We are going to use our first 2 kinematic equations to derive this equation. And last time, we decided, hey, we want to get rid of final velocity because final velocity is gross and we want to eliminate it. But this time, we're not going to do that. We're actually going to eliminate time. So first of all, I'm going to rearrange the second equation for time. So I'm going to subtract that v initial back over, okay? And then I'm going to go ahead and divide by acceleration in order to isolate time again, okay? We got v final minus v initial divided by acceleration is equal to time. And now, instead of replacing v final in the first equation, I'm going to replace time in the first equation. And so this whole guy, this red guy, is going to replace time here. So let's go ahead and see what happens. I'm going to still have my delta x on one side, my displacement is equal to 1/2 times v initial plus v final, bloop, times, whoop, big parentheses here, v final minus v initial on top, divided by acceleration, okay? Whew, that's a little messy. Let's see if we can make it a little nicer. Some of you may already see it. One thing I'm going to do here, just because I can, is I'm going to bring that a that's in the bottom over with the 2 that's in the bottom, right? They're both in the denominator of this big multiplication. So we can bring those guys over here. Then we are left with, I'm actually going to swap the order of v final and v initial in here to help you guys see something. Doesn't really matter because the order of addition does not matter, as we know. Whoops. And would you look at that? You might recognize it now. V final plus V initial times V final minus V initial. Guess what that is? Oh, right, that's the difference of 2 squares. If we go ahead and multiply this out, we're going to get V final squared. When I mean these two, I mean these 2 parentheses. If we multiply them out, over here we're going to get V final squared plus V final V initial minus v final v initial minus v initial squared. And guess what? These two terms, they cancel out, and we are left with the difference of two squares. So delta x is equal to 1 over 2a times v final squared minus v initial squared. Boom. And just to clean things up further, I'm going to multiply both sides of the equation by 2a. That's legit. And we have v final squared minus v initial squared on this side. And to top it all off, I'm just going to go ahead and add v initial squared to both sides and rewrite this equation so that it looks like this. Ta-da! We have v final squared is equal to v initial squared plus 2a delta x. So the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. And that, my friends, is our final fourth kinematic equation. Okay? So that's where the 4 kinematic equations come from. But let's talk about them a little bit, because why do we need all 4 of these guys? Why are all 4 of these guys so special? Well, there are a couple interesting things about these 4 kinematic equations, and you can write them down somewhere if you want to, but any physics class is going to give these 4 equations to you, so you don't need to memorize them. You just need to understand what they mean, okay? So let's take a look and take note on what these 4 equations have in common, all right? Well, one thing you may notice is they're all working with roughly the same variables, right? There are only 5 variables among these 4 equations. Take a look. Yeah, there's only 5 variables here. We got delta x. We got initial velocity. So we have displacement, initial velocity. We also have final velocity. We have acceleration, and we have time. And absolutely nothing else. There's not a single other equation here. And you also may notice that in each of these 4 equations, we're missing one variable. All of these equations have 4 variables in them, right? Each of these is missing a variable. The first equation is missing acceleration. The second equation is missing displacement. The third equation is missing final velocity. And the fourth equation is missing time, okay? All right, well, that's interesting. How does this help us? Well, it helps us a lot, actually. Let's say that we're looking for a variable, okay? Let's say that we're looking for, I don't know, let's say time, okay? Well, if we want to find time, we're going to use one of these equations to solve for it. Well, we definitely know we're not going to use the fourth equation because it doesn't have time in it. That's not very useful. So it's between the first 3 equations. And so it depends on what we're given. If the problem gives us our displacement, initial velocity, and final velocity, then we can use the first equation to solve for time. But if it doesn't give us the displacement, and instead it gives us the acceleration along with initial and final velocity, then we can use the second equation to solve for time. Or let's say it gives us displacement and acceleration, but it doesn't give us the final velocity, just the initial. Then we can use the third equation to solve for time. So these equations give us some flexibility and a lot of coverage here. And the deal here is that if we know 3 variables, if we know at least 3 variables out of this group, okay, out of this group, if we know 3 of them, then we'll be able to find the other 2, okay? We'll be able to find the other 2 for sure. We just need to know 3 of them. However, we need to know 3, okay? If we only know 2 of these variables, there's nothing we can do about it. And so, if you are working on one of these kinematics problems, one of these one-dimensional kinematics problems, and you're like, well, I only have 2 pieces of information, you're not looking hard enough. There's got to be some other piece of information in there. Because if there was only 2 variables given, you only had 2 givens, then you wouldn't be able to do anything. You'll always have at least 3 givens, and you just need to know how to find them. So let's go ahead and take a look at what solving a problem with one of these equations looks like, okay? And our problem-solving process is going to be kind of a four-step process here. And here's what the steps look like. The first step in solving a problem, after reading it, of course, is to draw a picture to represent the problem. Draw some kind of diagram, draw some kind of visual to help you visualize what's actually happening in the problem. Because you will be able to understand this problem or a given problem way easier if you can visualize it. Physics is a very visual science in nature. And so visualizing a problem and trying to understand it through a picture is a great way to understand what's actually going on and what variables are in play. There are actually studies to show that students who draw a picture at the beginning to understand a problem do significantly better on that problem than students who do not draw a picture, okay? There are studies to show this. We are scientists. We have to believe in our data. So if you are a physics student who believes in data, you will trust me when I say that you will do better if you draw a picture than if you don't, okay? I promise you. All right, so once we draw a picture, then we're gonna record our givens and unknowns. What three variables were we given, and what is our unknown? What variable are we trying to solve for? We're gonna use a little table to record that, and I'll show you guys how that works. Then, based off that information, based off our givens and unknowns, we're gonna choose an equation. We're gonna choose the correct equation for us, okay? And finally, we're gonna plug our numbers in and solve the equation. Sounds simple enough? Let's take a look and see how it looks in practice. And I'm going to be using one example problem here that is actually from a worksheet from my class. So if you're working on a worksheet in my class and this problem looks familiar, hey, watching this video really worked out for you then, because I'm about to do the problem for you, okay? So let's read the problem. A train starts from rest and accelerates slowly out of the station at a rate of 1 meters per second squared. If the train accelerates for 40 seconds, what is its final velocity? Okay, so let's start with step one. Let's draw a little picture here. Now I'm going to record everything I know in this picture. Okay, I'm going to draw a little train to start because we got a train, blip, 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 blip. And it's starting from rest. Okay. It's starting from rest, so I know that its initial velocity is 0, okay? We're starting from rest here. Boop. And then it accelerates slowly out of the station at a rate of 1 meter per second squared. So I'm gonna record that here too, 1 meter per second squared. And if the train accelerates for 40 seconds, what is its final velocity? What is its final velocity 40 seconds later? So what is that velocity? That's what we're trying to find, okay? So, cool, we have a picture. Now let's record our givens and unknowns in an organized fashion. And the way I like to do this is with a little table. Here's how I draw my table. Draw one line horizontal and then 4 vertical lines. Boom, just like this. And in each of these top cells here in this little grid, I'm going to write my 5 variables. There's displacement, there's initial velocity, there's final velocity, there's acceleration, and there's time. I kind of always write them in the same order. You don't have to, but it helps me stay organized. Okay? And so now I'm just going to go down the line and see what they've given me. Well, the train starts from rest. And so we know the initial velocity is equal to 0, so I'm going to record that in my table. Initial velocity, 0. That's one of my givens. Okay? Another one of my givens, acceleration is 1 meter per second squared. So I'm going to record that guy in here, 1 for acceleration. By the way, if you're wondering how we got initial velocity of 0 for train starts from rest, just think about it. If I am starting from rest, all right, if I am at rest, that means I'm not moving. Rest means you are not moving. And so if you're not moving, then your velocity, your speed is 0. So if you start from rest, your initial velocity is 0. Okay? If you come to rest, then your final velocity would be 0. So it's a little keyword. From rest is a little telltale word. So if you notice that you only had 2 numbers in this problem, and you're wondering where your third number is, it's hidden with some keyword like from rest or something like that. Okay? All right, and then finally, the train accelerates for 40 seconds. So our time here is 40 seconds. Okay? And it asks, what is its final velocity? So it's asking me, what is the final velocity? So I'm just gonna write v final down here, okay? Because this is the variable that I'm solving for. I'm gonna write it again. If you want to, instead, you could just write a question mark here. Yeah, that's fine too. So we're looking for final velocity, and we were given initial velocity, acceleration, and time. All right, and we have nothing to say about the displacement. So there's no information. We're not looking for it, but we also weren't given it. And so we're gonna look for the equation that has these 4 variables, because these are the 4 variables we care about. So we're gonna be looking for the equation without displacement. And which equation does not have displacement? Oh, look at that. It's equation 2. So we're going to choose equation 2. See how that works? All right. So let's try it now. Let's use equation 2. So I'm going to write equation 2. It's my next step. V final is equal to V initial plus acceleration times time. Always write out your equation, okay? And now I'm going to rewrite this equation, except I'm going to plug in all my values. Well, let's start with V final. V final is what we're solving for. So because it's what we're solving for, it's our question mark, I'm just going to leave it as V final, okay? It's the variable we're solving for. V initial is 0, so I'm going to replace my V initial in this equation with 0. Acceleration is 1 meter per second squared, and our time is 40. Now I could include my units, but I don't have to because I know that all my units match. I have meters for all my distances and seconds for all my times, right? Acceleration is in meters and seconds. Time is in seconds. So my velocity will be in meters and seconds. Okay, so V final is equal to 0 plus 1 times 40. And for those of you that are wizard mathematicians out there, you'll know that this is equal to 40. 40 what? Well, it's a velocity, so meters per second. If your units don't match, let's say some of your units for time are hours and some are seconds, then you're gonna have to do a little bit of conversion. But because they all match, we can just work with our meters and seconds, and we are happy because that is the answer to the problem. Our final velocity is 40 meters per second, okay? Boom, there's one. So let's do one more, and I want you guys to pause the video and do this, try and do it on your own, okay? And if you can't do it on your own, that's okay. We'll go step by step and I'll have you follow along with me, okay? So if you want to try it on your own, go ahead and pause the video now. Otherwise, I'm going to go ahead and get started. So example problem number 2. We have a driver in a car that sees a dog in the road, and the driver starts braking when the car is 15 meters away from the dog. As I read this problem, I'm going to draw my picture, okay? I'm going to draw my picture as I'm reading. So we have a driver in a car, a great car, sees a dog in the road. All right, here's my little puppy. Little puppy dog. And the driver starts braking when it's 15 meters away from the dog. 15 meters away, okay? And if the brakes slow the car down at a rate of negative 0.75 meters per second squared, meters per second squared, that unit tells me that this is an acceleration, so negative 0.75 meters per second squared because of the brakes. Then what is the maximum initial velocity at which the car can travel without hitting the dog? Oh, okay. Well, I've been given 2 numbers. I was given 15, I was given negative 0.75, but where's my third number? Do you see it? Take a moment, pause the video, see if you can find where the hidden third number is. All right. If you've given it a shot, well, the hidden third number is in the phrase without hitting the dog, right? What is the maximum initial velocity that the car can travel without hitting the dog? If the car doesn't want to hit the dog, it has to stop before hitting the dog, right? It has to stop right before it hits the dog. So that means the final velocity of the car, if it stops, has to be 0. In a stretch of 15 meters, right? Over the course of 15 meters, we're gonna have to stop and not hit the dog. All right, our final velocity must be 0. And so what is our maximum initial velocity? Well, it's time to hop over to the table here. A very poorly drawn table. We got a lot of space for acceleration and time in this one. All right, so our displacement we know is 15 meters, right? The car starts 15 meters away from the dog. So if it doesn't want to hit the dog, then it's going to have to travel exactly 15 meters away, just shy, okay? So we'll say 15 meters is our displacement. Our initial velocity, well, that's what we're solving for. We're looking for the maximum initial velocity. We're finding the maximum because we're assuming that we're stopping exactly 15 meters away from where we started, just in front of the dog. Our final velocity is 0, and our acceleration is negative 0.75. And no mention of time here. We don't care about time. So now we need to find an equation with these 4 variables. We need to find an equation without time. Do you see it? Pause the video, see which equation you think we're going to be using. And we are going to be using equation number 4. Right? Equation number 4 does not include time here. No time to be found. So let's go ahead and write that equation down here. The final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. Okay. Alrighty. And so we have our equation. Now we're just going to go ahead and plug in our values. Final velocity is 0. So we have 0 for final velocity squared is equal to initial velocity. That's what we're solving for. So we're going to leave it as the initial. We're going to leave that variable there as what we're solving for. Plus 2 times the acceleration, negative 0.75. By the way, am I in meters and seconds for everything? Well, my distance is in meters. My acceleration is in meters and seconds. My final velocity is 0, so units don't really matter. So yeah, we're good. We're good. We got meters and seconds. Okay. And now displacement is 15 meters. Cool. Okay. So now let's do a little bit of math here and simplify everything. Well, 0 squared, that's a tricky one. 0 is equal to v initial squared plus, well, actually, let's get rid of that plus. It's going to be a minus now, right? We know it's going to be a minus. So minus 2 times 0.75 times 15, which I believe is going to be 22.5. Okay, get 22.5. So v initial squared minus 22.5 is equal to 0. So if I add 22.5 to both sides of the equation, I'm going to get that 22.5 is equal to v initial squared. But we're not done. We want v initial, not v initial squared. So we got to get rid of that squared. How are we going to do that? Just going to square both sides of the equation. Okay? I'm going to square root both sides of the equation, rather. And we're going to get that v initial is equal to the square root of 22.5, which is equal to 4.7. All right. 4.7 meters per second. And there it is. Simple as that. Okay? All right, that is our final answer. Our initial velocity is 4.7 meters per second. So, to recap, in order to solve these problems, draw your picture first. Try and understand all the variables in play beforehand before we log them in our table. Then we create our table and log our 5 variables. we're going to know 3 of them, we're going to be looking for 1, and 1 is going to be totally irrelevant to the problem. And we're going to look for the equation without that irrelevant variable. So in this case, it was time. Look for the equation without time. Then finally, write down your equation and just plug the numbers in and solve for that variable. Everything else should be a number, okay? You should only have 1 variable in your equation once you have plugged in. So that's all for today. I hope you guys have a wonderful rest of the day, and I hope these problems go smoothly for you guys. So peace. Take care.